In this lesson, we are going into a new chapter, that is the planar kinetics of rigid body, and we are talking about work and energy. So let's take a look at the whole chapter of planar kinetics of rigid body. We have covered previously the force and acceleration, where we make use of the second Newton law of motion that states that F is equal to ma. And also we have the equation for rotation. The sum of moments is equal to the mass moment of inertia I multiplied with the angular acceleration of alpha. In this chapter, we are talking about a new method to calculate the parameters required in planar kinetics of rigid body, where we talk about work and energy. So in this chapter, we are going to learn about kinetic energy, that is denoted by the symbol T, the work done, denoted by the symbol U, and we are going to talk about the principle of work and energy. Let's take a look at the kinetic energy. The kinetic energy T is given by these two terms here. 1/2 times the mass times Vg square. Vg is the velocity of the center of gravity, plus half Ig, mass moment of inertia, about the center of gravity, times omega square, where omega is the angular velocity. So the first term basically represents the translational kinetic energy. The second terms represent the rotational kinetic energy. And remember the type of motion a rigid body can undergo. There are three types of motion, and let's say if there is only translation that is being experienced by the rigid body, therefore definitely the omega becomes 0 because the rigid body does not rotate, and the kinetic energy is only equivalent to half mvg square for the case of translation. For rotation about a fixed axis, say the rigid body is now fixed or pinned at point O and it is currently rotating about point O, then the kinetic energy will have both terms, the translational terms half mvg square, and also the rotational terms half ig omega square. If we calculate the kinetic energy about the center of gravity, and if we calculate it about point O, about the center of rotation, then the kinetic energy becomes half IO omega square. No more translational terms if we calculate the kinetic energy about the center of rotation O. If we calculate the kinetic energy about center of gravity G, we will have both translational and rotational terms. In the case we calculate the kinetic energy about point O, we need to calculate the value of IO. IO is the mass moment of inertia of the rigid body about the center of rotation. IO, of course, can be calculated using the parallel axis theorem that states IO is equal to Ig plus md square. Ig is the mass moment of inertia about the center of gravity. M is the mass of the rigid body. D is the distance between point G and point O. In this case, this is equal to Rg. That is for rotation about a fixed axis. For general plane motion, of course, to calculate the kinetic energy, we need to consider both terms as well, because general plane motion is the combination of translation and rotation. So the translational terms half mvg square is there, and also plus the rotational term half ig omega square. And remember from our previous lesson, for general plane motion, if we are able to locate the IC, the location of instantaneous center of zero velocity, then we can calculate the kinetic energy of the rigid body about IC. And remember, IC is as if the rigid body is making a pure rotation about IC. So now T can also be calculated using half IIC omega square. And same like the rotation, IIC can also be calculated using the parallel axis theorem, where IIC is equal to IG plus MD square. And remember that the kinetic energy is always positive. It is always positive because the mass is positive. There is no such thing as negative mass. And also the mass moment of inertia is also positive, must be positive. V can be negative, but since V is squared, and also omega can be negative, but because omega is squared, and therefore the kinetic energy must always be positive. That is about the kinetic energy. Now we go to the work done. Work done is symbolized by capital U. U is the symbol for work. The definition of work is a body will do work when it undergoes displacement in the direction of the force. There are a few forces that causing the body to do work. Let's take a look at the work done by a force. The first case is that we have a variable force. Let's say the force, the magnitude of force is changing as the rigid body is moving. So if we have a variable force, then we need to use the integration to calculate the work done by the force. Here UF is equal to the integration of F dr. R is the change of position of F, and this can also be rewritten as integration of F cos theta ds, as being the displacement of the rigid body. If we have a constant force that acts at an angle to the displacement of the body, then the work done by the force UF is now equal to F cos theta, because we have to calculate the component of the force in the direction of motion, in the direction of the displacement. Therefore, F cos theta times the displacement S, how far the rigid body has traveled. And if theta is equal to 0, which means that the force is acting on the same line, on the same direction as the displacement, therefore UF is then equal to F times S. This is the most common form of the work done by a force. The work done by the force is basically the force times displacement S. Now, the work done by the weight can also do work, because the rigid body can travel from in y-axis from top to bottom, for example. So UW, the work done by the weight, is given by the equation minus W minus the weight times delta Y. Delta Y is the displacement in y-axis. So if the displacement is upward, for example, if we have a ball, for example, if we have a ball thrown up, so the ball actually travels from bottom going up, that the displacement is upward, therefore the work done is negative, because delta Y is negative. So minus W times delta Y is positive. So minus W times positive delta Y will give a negative work done by the weight. But if the displacement is downward, which is the normal case, where the rigid body travels from top to bottom due to the weight, therefore the work becomes positive, because here is minus W, and delta Y will also be minus because it is traveling from top to bottom. So minus minus cancel out each other, then the work done by the weight becomes positive. There is also work done by spring. So spring can be stretched or can be compressed. So this, let's say the unstretched length of the spring is given by S. So if the spring is being compressed, then this is the new length of the spring, S1. If it is being stretched, then the new length of the spring is S2. So in both cases, compressed or stretched, the work done by the spring is negative, because the displacement of the body is in the opposite direction of the force. If you compress a spring, then the force will be acting in the opposite direction of the force given. If the spring is stretched, the spring will try to go back to its original position, and therefore the force is also in the opposite direction of the displacement, and therefore the work done by the spring is negative, and it is given by this equation here. US is equal to minus half KS2 square, the final length of the spring square, minus half KS1 square. KS1 is the initial length of the spring. So this is the equation to calculate the work done by a spring, by a compressed or a stretched spring. There are also a few forces that do no work. For example, the forces that act on a fixed point on a body. An example of this kind of force is a reaction at pin support about which the body rotates. For example, we have a rigid body here, pin connected at point A, and it is rotating with an angular velocity of omega about point A. Point A is the center of rotation. At point A, at the pin, there will be reaction forces in X and Y axis. And because this point doesn't move, it is just the center of rotation, therefore no work done by AX and AY. Remember, for work to be done by a force, it has to have the displacement. Okay, remember the definition of the work done is a body will do work when it undergoes displacement in the direction of the force. Okay, that is the reaction at pin that is not doing work because this point doesn't move. We can also have forces that have direction perpendicular to the displacement. It is not in the same direction as the displacement, but it is perpendicular to the displacement, which in the end makes these forces do no work also. For example, the normal reactions acting on a body and also the weight. You can see here, if the rigid body is traveling from this point to this point, then the displacement is in the horizontal direction, in X direction, in X axis, and the weight and the normal force is acting in Y axis, and there is no displacement in Y axis. The displacement occur in X axis only. Therefore, in this case, the weight and the normal force does not do any work throughout the motion of this rigid body. That is what it means by the force that have direction perpendicular to the displacement. See, the displacement is in X axis. The direction of the force is in Y axis, that is 90 degrees to the displacement. Therefore, the weight and the normal force here do not do any work. And also friction forces, friction force acting on a body when it rolls without slipping. When it rolls without slipping, from our previous lesson, we know that the contact point here is the location of IC. Because at this particular point, the velocity is equal to 0, and therefore the work done by the friction force in the case of rolling without slipping is also 0. So no work done by the friction force here. So these are a few examples of forces that do no work throughout the motion of the rigid body. Now the couple moment can also do work. The reason being it is called couple moment is that the couple moment can be illustrated as two forces acting on opposite direction with a distance r here. So this is representing the couple moment, and therefore to calculate the work done by the couple moment, if the couple moment m is a variable moment, which means that it change value throughout the motion, then we have to use integration from theta 1 initial angle to the theta 2 final angle, integrate of m d theta. And if the couple moment m has constant magnitude, it does not change throughout the motion, then simply the work done by the couple moment um is equal to the couple moment multiply with the change of angle, and please make sure that the angle is in radian, it is not in degrees. Okay, let's take a look at an example here. We have a rigid body rotating, and it is connected to a spring, and the spring here remains vertical because the spring can slide within this slot here. So the bar shows has a mass of 10 kg. Bar AB, bar A here, bar A here has a mass of 10 kg, and it is subjected to a couple moment of 50 Newton meter. So there is a couple moment here. This blue couple moment here has a value of 50 Newton meter, and a force of P 80 Newton at the end, which always applied perpendicular to the end of the bar. So the force here is always perpendicular, it's always 90 degrees to the bar. The spring has an unstretched length of 0.5 and remains in vertical position due to the roller guide at B. Determine the total work done by all the forces acting on the bar when it has rotated downward from theta equals to 0 degrees. Initially, the bar is here, theta equals to 0. So initially the bar is in this position, straight, and then the final position is theta equals to 90 degrees. So this will be the final position of the bar. So this will be position number 1, this will be position number 2 of the bar. So we're gonna calculate what are the work done by this bar that has this motion. So first we're gonna draw the free body diagram. So at point A we have the reaction forces AX and AY. We have the couple moment 50 Newton meter. We have the weight pointing down 98.1 because the bar has a mass of 10 kg. We have the spring force, which is unknown. We don't know what is the value of the spring force here. And also we have the constant force P of 80 Newton. So let's calculate the work done by the weight. Since the weight is 98.1 Newton and is displaced downward 1.5 meters. So basically the center of gravity is over here initially. This is point G, and this is the final position of the center of gravity. So to find delta Y, to calculate the displacement, this will be delta Y. So here will be delta y. This is the value of delta y. So from here, going down here, this will be negative because we define our axis like this. Okay, this is positive x and this is positive y. So going down is definitely negative. So the length of the bar is 3 meter. So going down here, which means that delta y is half of the bar, that is equal to 1.5 meter. That's why it's 1.5 over here. Okay, and therefore the work done by the weight is minus W. So this should be minus here. This should be minus. So minus 98.1 times minus 1.5 meter. That's why we got a positive value of 147.2 joule. Remember, the unit for work done is joule, and also the unit for kinetic energy is also joule. Next, let's take a look at the work done by the couple moment here. There is a couple moment M of 50 Newton meter. The couple moment rotates through an angle of theta equals to pi over 2. Remember, the motion is from theta equals to 0 until theta equals to 90 degrees. So 90 degrees here is equivalent to pi over 2. Okay, we have to convert degrees into radian. And therefore, the work done by the couple moment is equal to 50 Newton meter times pi over 2. We have 78.5 joule for the work done by the couple moment. Next is the work done by the spring force. Initially at theta equals to 0, the distance here, the distance of the spring at this position, this will be the spring. This will be the spring at this position, and the length of the spring here is 0.75 at position 1. So it says here that the spring has unstretched length of 0.5, which means that initially at theta equals to 0, the spring has already been stretched. Therefore, at theta equals to 0, the S1, the length of the spring, the stretched length of the spring is 0.75 minus the unstretched length of 0.5. So we have 0.25 at position 1. And when theta equals to 90, the stretch is now at this position. The spring is at 2 meters. 2 meters. So basically the spring might be somewhere over here. So from here to point A is 2 meters. This is 2 meter here. And then we have to plus with the distance up here, that is 0.75. So in total we have 2 meter plus 0.75. This is the length of the spring, and we have to minus or subtract with the unstretched length of 0.5. Therefore, S2 becomes 2.25 meter. And when we have the value of S1 and S2, so this is basically S1. This is S1, and this here is S2. So we can straight away substitute in the equation. In the equation, to have US is equal to half times 30. 30 is the stiffness of the spring, is given here. K is the stiffness of the spring, 30 Newton meter, times 2.25 square, S2, minus half times 30 times 0.25 square. That is S1. So this is S2, this is S1, and over here is the K, the spring constant or the stiffness of the spring. Okay, so we have minus 75 joule, and remember from our previous slides that we have identified or we have defined that the spring force must always be negative regardless whether the spring is being compressed or it is being stretched. Okay, next we calculate the work done by the force P here. So the force P acts at the end. So initially the force P acts at this point, P, and finally the force P is acting at the end here. So we can draw the displacement of force P is something like this. It is like a quarter circle. This is the displacement S of force P. So since we have this angle here 90 degrees, we can calculate the displacement S by using the equation S equals to R times theta in radian. So in this case, R is the length of the rod, that is 3 meter. So R here becomes 3 meter. So R here is 3 meters. And theta here is basically pi over 2. We have to convert it to radian. So this is pi over 2. That is basically 90 degrees. So we have here the displacement of the force P is pi over 2 times 3. We have 4.712 meter. This is the displacement. And the work done by the force is simply the force 80 Newton times the displacement. So 80 times 4.712, we have 377.0. So this, we have covered this, we have covered this, we have covered the weight, we also have covered the moment. Now AX and AY, we have already explained in the previous slide that the forces AX and AY are not doing any work because they have no displacement. They are static at this position, so no displacement of AX and AY, therefore no work done by these two forces. So in total, we can calculate the total work done by all the forces acting on the bar here. So we have 147.2 plus 78.5 from the couple moment minus 75 from the spring force plus 377 from the force P. Therefore, we have the total work done is equal to 528 joule. So that is how you calculate the total work done by the forces acting on a rigid body. Okay. Next, we will go into the principle of work and energy. Remember, previously we have discussed about the kinetic energy and also the total work done. So the principle of work and energy states that the initial kinetic energy plus the total work done is equivalent to the final kinetic energy. So T1 is the initial kinetic energy. Sum of U1 to 2 is basically the total work done for the rigid body to move from point 1 to point 2, from position 1 to position 2, or from the initial position to the final position. The summation of these two terms is equal to the T2, which is the final kinetic energy of the rigid body. So in words, this equation states that the body's initial translational and rotational kinetic energy, T1, plus the total work done by all external forces and couple moments acting on the body as the body moves from its initial to its final position, this here, sum of U1 until 2, is equal to the body's final translational and rotational kinetic energy, that is T2. So this is what is known as the principle of work and energy. And this is why we need to know how to calculate the kinetic energy of the body in motion and also the work done by external forces on the rigid body. Let's take a look at an example of how we can make use of the principle of work and energy. So here there is a 30 kilogram disc shown is pin supported at its center. So there's a pin support here. We want to determine the number of revolutions it must make to attain an angular velocity of 20 rad per second starting from rest. It is acted upon by a constant force F equals to 10 Newton here, which is applied to a cord wrapped around its periphery, and a constant couple moment, that is a constant couple moment of 5 Newton meter. Neglect the mass of the cord in the calculation. So first, we need to calculate the kinetic energy. And since it says that the rigid body starts from rest, it says that it is starting from rest, therefore the initial kinetic energy is equal to 0. T1 is equal to 0 simply because it starts from rest. Okay. T2 is equal to 1 over 2 IO omega square. You can also write as IG because apparently point O and point G is now at the same point. So IO is taken for a disk. This can be, you can refer to the table of mass moment of inertia, half mr square. This is m of the disk, and this is the radius of the disk. So half mr square is IO. 1 over 2 is from here, and omega, it is given, omega is equal to 20 rad per second. So we have T2 is 120 joule. Now we have T1 and T2. Remember the principle of work and energy. We need to calculate the sum of work done throughout the motion. So when we calculate the work done, there are two work being done here. The first one is by the couple moment, M is equal to 5 Newton meter. What we want to find out here is the number of revolution is basically the angle theta that this thing has rotated. So this is the one that we want to find out. Therefore, the couple moment M is equal to 5 times theta. Theta we don't know yet. And for constant force F here, we will use the same equation like our previous example. S is equal to R times theta. Okay, in this case, R times theta. So F is 10 times R times theta. We don't know what is the value of S yet because we don't know what is the value of theta. So R is given as 0.2. Therefore, we have the work done by the constant force F is equal to 2 pi, is equal to 2 times theta joule. Then we can apply the principle of work and energy. T1 plus sum of work done is equal to T2. So we have T1 equals to 0. M times theta is 5 times theta plus F times S is 10 times theta times 0.2. This is what we have calculated up here, is equal to T2, that is 120 joule. So we got a value of theta equals to 17.14 rad. And from this, we can convert it into revolutions by calculating 1 revolution is equivalent to 2 pi rad. 1 revolution is 360 degrees, that is equal to 2 pi rad. So we can convert from rad into revolution. So we have in the end the number of revolution it must make to attain an angular velocity of 20 rad per second is 2.73 revolutions.